We're going to be considering this question 16 out of Gunning's An Introduction to Analysis. It's about the trace of a matrix, and it's in the linear algebra subsection. It reads as follows. The trace of A of an n by n matrix is defined to be the sum of its diagonal terms. 1. Show that the trace of A plus B is equal to trace of A plus trace of B, that trace of AB is equal to trace of BA, and that trace of ABA inverse is equal to trace of B if the matrix A is invertible. 2. Is trace of AB equal trace of A trace of B? Why? 3. Show the equation AB minus BA equals I has no solutions in n by n matrices AB over field F, provided that n does not equal 0 in F. Alrighty then, so take a couple seconds to try this out for yourself, then we'll do some hints, then we'll get on with the proof. Alright, now that you've tried it out for a little bit, let's do some hints. The first hint is that you should always try to use previous results in order to continue to solve this problem. So for instance, if you have a section and you don't know what to do, you should try seeing if any of the previous results you proved will help it. In particular for 3, this equation seems very vague and doesn't seem like it has anything to do with the trace, so you need to introduce the trace somehow. There are other places where this applies to, though. Alright, let's begin the proof. So the first one, let's proceed as follows. So the trace of AB is equal to trace of A plus trace of B. Let's let AB equal some matrix C, and to find the trace of C, we're going to take the sum over its diagonal entries from 1 to n of CII. But if we recall how the terms of C are defined, we say that Cij is equal to Aij plus Bij, because for matrices, matrix addition is defined element-wise. Therefore, this equals the sum from 1 to n of Aii plus Bii. Then we apply the property of sums, that this is the sum from 1 to n of Aii plus the sum from 1 to n of Bii. However, we'll note that this is just the trace of A plus the trace of B. So we're done. Next, let's check the second property. Show the trace of AB is equal to trace of BA. Let's denote each of these matrices as C and D respectively, and then let's look at their diagonal entries. You can check by the definition of matrix multiplication that, first of all, note that A and B must be square in this case, otherwise the second product would not be well defined. Actually, you can have them non-square, they just need to be non-square in such a way that it's n by m by m by n, but you see that these traces will have different dimensions, such that you get a m by n times n by m on the right side. So C and D need not have the same size. If they have the same size, it's a little easier for imagining this, in that they're both square matrices, so it'll be easier, but it need not be the case. In particular, we'll note that we'll remember the definition that for an m by m matrix times some m by, in this case it'll be n matrix, to get an element in the product matrix, for instance this first element, you need to take the product of the first row times the first column and then add them pairwise. So if we consider the ith element along the diagonal, which is what we care about for the trace, we'll see that Cii, where C is going to be AB, is equal to the sum, and since this inner term has it is an m long row, or this first matrix has m columns and the second one has m rows. This sum from, let's call this index perhaps j, from 1 to m of, and then we take the first row, or in this case we're taking the ith element, so this can be the ith row, so Ai j times b, and then we're going to need to match them, so it should be bji. So that's the nth element of this row. Next, let's do the same for dii, and we see this can be the sum. In this case, since we're going to be considering these in opposite order, we're actually going to sum from, let's say, k equals 1 to n of, let's call this, and by the same logic as before, this bik AKI. So here are two sums. Next, let's check the trace of C. trace of C is equal to the sum. Well, let's check how many terms are in the sum. This was an n by n matrix in our product. So therefore, this is going to be a sum from 1 to n of each of the CIIs. But we know each of the CIIs is going to be, let's call it I equals 1. Is going to be this respective sum. So this is the sum from 1 to m and the sum from j from 1 to m of aij bji. And next checks the trace of D. Well, since this one is an m by m matrix, and we consider the trace as the sum over the m diagonal entries, so it's from 1 to m, and then the sum from 1 to n of bji aij. With that, we see these are actually the same sums, since we can re-index them and we can reorder them, and we'll get that these are the same. With that, we see that these traces are equal. For instance, note that if you commute the two sums, since they're finite sums, you can get the exact same thing by just re-indexing from j to I or I to j or the k from before, since we've dropped that now. See, these two sums are the same. And you should explain that a little more deeply, but that is basically that idea. For the third part, we can actually just use the part we've just proved. In particular, let's let A times B equal some matrix C. Then we're looking at the trace of CA inverse. By our previous result, we know this equals the trace of A inverse C, and note that we need all the dimensions to work out since we need B to be square, so and then A is definitely square since it's invertible. But then A inverse C is equal to the trace of A inverse AC, which is just equal to the trace of C. I'm sorry, A inverse AB, which equals the trace of B. So we've shown that our starting thing is equal to this if the matrix A is invertible. With that, we're done with part 1. For part 2, we're going to say that no, the trace does not split over products. And the way we can prove this is by saying, hey, let's just prove by counterexample. Note that the trace of some identity matrix of size n, we'll call that I sub n, is equal to n because it's a sum of 1s for n times. So the trace of in times b is equal to the trace of b does not equal n trace of b, since we're assuming it does not equal n trace of b if n is greater than 1. If n is greater than 1, this equation is not true. If it is true, this is simply a statement about the commutativity of scalar multiplication. So it's pretty trivial. So for n bigger than 1, this is not true, but this, as we've noted, would be the trace of in times the trace of b. So therefore, these need not be equal. Finally, let's do the third one. We're going to show that this has no solutions. And when we do that, let's assume that it did exist. Well, if it did exist, then the traces would be equal, right? Because if two matrices are equal, then their traces are equal. The trace of the left-hand side, AB minus BA. We can apply our results from 1 to get this as the trace of AB minus the trace of BA. And let's also recall our other thing, where let's assume these have size n. Then the trace of I is equal to n. So these should be equal if it was possible to solve this equation. But this, by our previous result, trace of BA is equal to trace of AB, so this side is 0. That implies equals n, but we specifically assumed n does not equal 0 in f. Therefore, we have a contradiction, so our assumption that AB minus BA equals I has any solutions is false. With that, we're done. Thank you for watching.